Now, in this section, we're gonna talk about chemical bonds, how different atoms can make bonds, how they can join up with different atoms, and then the types of different bonds that they can get into. So let's go ahead and start on this 5.3. Here's our vocabulary for this one. These are the terms we'll be going over by the end of the video. So here we have valence electrons, the octet rule, Lewis dot structure, ionic bond, covalent bond, metallic bond, intermolecular forces, polar bond, nonpolar bond, and a hydrogen bond. Now, as a quick little review, I know that we've been over this before, but the valence electrons are those electrons that are in the outer shell of an atom. So we can know how many valence electrons are for each atom based on what column they are in the periodic table. So remember that the transition metals and the inner transition metals, they have very weird properties. They're really funky, and it makes this a lot harder for us. So we're just going to keep it simple. We're going to ignore those and just focus on the main series elements. So the way we can know the valence electrons for each of these main series elements is just the number column that they come in when you start from the left. So everything in this first column has one valence electron. Everything in this second column has two valence electrons. Third column is 3, fifth column is 5, seventh column is 7, and so on. The only exception to this one is helium in the top right. It's in the eighth column, but it will only have two valence electrons because helium only has two protons and can only have two electrons. Now, in nature, a lot of these elements that we see, they're always part of something else. They're always in a compound of some sort because when our elements, the way that we know them on the periodic table, in their ground state, they have unfilled outer orbitals. And this actually makes those electrons very reactive. They want to do something, they want to get somewhere. And so that's not very good for keeping a pure sample of an element. The exception to that are the noble gases, all the way on the right side of the periodic table. So let's look at one of these and see what's going on, why they're the exception to this rule, where most elements they're combined with something else, but the noble gases are not. So if we look at a diagram of neon, we only have two energy levels, and we want to focus on the outer one. This is where the valence electrons are. So let's go ahead and count them. So if I start from the top, that's my first one. The one next to it is 2. So we'll just go around the ring, naming these 3, 4, sorry, counting these, not naming them. 5, 6, and then 7 and 8. And so this is true for all of the noble gases except helium, because again, they're in that eighth column, eighth column in the periodic table. So that's true for all the noble gases. They all have 8 valence electrons. And what we see is that actually 8 is the maximum number of valence electrons that we can have. So in this graph over here, we get to 8 on the right side, and then we start over with 1 on the next row. All right. So that's actually called the octet rule. And this is what dominates all of our predictions for, what types of compounds we can make. And then this a very important concept to chemistry, and it's so important that I'm going to put a box around it just so that you don't forget it. All right. And so atoms that have 8 electrons, they have a full octet, and they're actually, in terms of energy, they're very stable, and it takes a lot before they will react. We have to manipulate them in a lot of ways to get them to form compounds. Now that we are talking about compounds, we need to first start with how to write them so we can make sense of them later. So what we need to know for now is that to make a compound, atoms will react, and when they do that, they're either trading or sharing their valence electrons. And the way that we can keep track of these valence electrons and know where they go, know where they are at all times, is that we use what is called the Lewis dot structures. So this is named after Dr. Gilbert Lewis, who was a research chemist from the early 1900s. And as impressive as all his work in chemistry was, his Lewis dot structures are actually really easy to use because all they tell us is basically the valence electrons being put around a chemical symbol. So let's actually build one now so we can see what they're all about and what they show us and how we can use them. All right, so now when you are building your Lewis structures, you just need to follow 3 easy steps to get it right. So let's do this example for carbon. The first thing we need to know for carbon is its element symbol. So for carbon, very simply, it's just C. So we'll just write a nice C to start our Lewis dot structure. What's next is that we need to know how many valence electrons carbon has. So if you check it on the periodic table, carbon, it is number 6 on the periodic table, but it is in the 4th column of the periodic table when we ignore the transition metals. So now carbon will have 4 valence electrons, and I'm going to be abbreviating valence electrons as just VE to make it a little bit easier. So don't get confused by that. All right, but now all right, step 2, we know that carbon has 4 valence electrons, and all that's left is step 3. We just need to fill in the valence electrons around the symbol using dots for our electrons. So when you do this, just to keep this very neat and organized, imagine there's a box around your symbol. Don't actually write this box, but just imagine that it's there. And so we have 4 sides to this box. So we have 4 sides that we are going to put our electrons in. And we'll just go in order, start with 1 on each side before you start to double up. So in this carbon, we have 4 valence electrons, and we'll put them around the C on the top, sides, and bottom of the chemical symbol. So this is what our final Lewis dot structure for carbon will look like without the box in the center. All right. So again, very important is that start with single electrons on each side before you start to double up, and this will make it easier to predict what atoms will fit together, kind of like puzzle pieces. All right, and so if here is a table that you can use as a reference to see all the different elements, and this is just really elements 1 through 20. We're just sticking with the simple ones for this. So again, we're skipping over the transition metals. Those are difficult. So it's 2 ways that you can do this. You can either memorize how to build your own Lewis structures just from knowing where they are on the periodic table, or you can actually memorize the Lewis structures for each of these 20 elements. So whichever one you think is easier, I think you should go for it. And so one more thing to go along with these Lewis dot structures. Remember that I said that you should put in single electrons around the sides before you start to double up. So I just wanted to show you this in action. So again, if we take carbon, the one that we made where we have 4 valence electrons around it, if we move on to the next one, nitrogen, we'll just be adding 1 more electron. But notice that nitrogen has 3 single electrons and 1 double. So if we go in order here, boron will only have 3. Move on to the next one. Carbon will have 4. And again, this takes care of the 4 single sides. And then nitrogen is when we finally start to double up on the Lewis dot structure. And we can go one more and actually use our Lewis dot structures to build chemical bonds. All right, so let's go ahead and use an example to see how this would work out. So let's take just a very simple molecule of water, good old H2O. So when we are drawing our chemical bonds for our Lewis structures, we need a Lewis structure for every single atom in that molecule. So if we're looking here at H2O, we know it will have 2 hydrogen atoms. Each of them will have 1 valence electron, and then I will also need 1 oxygen atom, this one with 6 valence electrons. So now these are my pieces that I am working with. I need to somehow connect them all together so I don't have any single electrons left over. So I'm going to copy my oxygen over on this side, and you'll see why I would prefer to start with oxygen instead of hydrogen in just a second. All right, and then I would want to pair up these single electrons in oxygen. I want to pair them up with the single electrons in hydrogen, because when you make a chemical bond, you are pairing up 2 electrons from 2 different atoms. So when I do that, notice that this oxygen will have 2 slots where we have single electrons. Hydrogen has each hydrogen will have 1 single electron. So I can just go ahead and pair them. If I just take this hydrogen atom and shift it over to my right side, it will fill in that gap that I have in the oxygen on the left. Then I can take the bottom hydrogen and put it on the bottom of my oxygen. And so you can see here that oxygen started with 2 sides where we already had paired electrons. And then the empty ones, I filled them in with the single electrons from hydrogen. And so those are what represents my chemical bonds when I have 2 electrons in between 2 atoms. Now, when we have a full Lewis dot structure, and And in order to be correct, every atom around needs every atom needs to have a full octet that need full orbitals in order for them to be stable. So if we look through here and focus first on the oxygen, see what electrons are surrounding. If you count them through, you'll see they have 1, 2, 3, and 4, 5, 6, 7, and 8. Oxygen does have 8 electrons around it, so it does have a full octet. It will be very stable. But when it comes to hydrogen, if you look to the sides, there's nothing except for what's on the right. That is 1 and 2. And same thing for this hydrogen, only gets 1 and 2. And this is actually an exception. Hydrogen will only need 2 electrons because it doesn't have enough protons to hold on to 8 electrons. It only needs 2 to have a full octet. All right, so this actually brings up this whole list of elements that are a little bit of an exception because most atoms, they can form at least 2, 3, sometimes even 4 bonds. But for these elements, hydrogen and the halogens, so basically fluorine, chlorine, bromine, and iodine here on the 7th column, they can only form 1 bond. And the reason for that is that they will only have 1 free electron they can create bonds with. And so when we actually start building our Lewis dot structures and you start to get a little bit of practice, you'll see that some atoms already have paired electrons that they can't use for bonding.